Sequences in series. Today we're going to continue with what we were just talking about the limits the other day, and we're going to talk about sums of infinite series that go on forever and ever and ever. And that might sound kind of weird to you because let's take a series that goes on forever. Let's take 1 plus 2 plus 3 plus 4 plus 5 plus 6 plus, okay, I'm getting tired, dot, dot, dot. It's going to go on forever. This is arithmetic. This is an infinite arithmetic sequence. And actually, it's an infinite arithmetic series, right? Because those are plus signs in there. It's infinite arithmetic series. Well, guess what? That adds up to infinity. Okay, if we keep adding these, we're going to be adding infinity and infinity and infinity and infinity, and it's going to grow without bound. Grows without bound. Hopefully you remember a term we use for that called diverging. Okay, it diverges. It does not converge and add up to one finite number. It diverges. Okay, so let's look at maybe another kind of sequence, an infinite being as this is sums of infinite series. And let's look at geometric. Because I think you can see that every arithmetic will add up to infinity or negative infinity, right? If we're decreasing by 1 or decreasing by 10, right? And we get to negatives, we'll be at negative infinity. So let's look at a geometric one. Geometric. Let's take 4 times 2 to the n. Okay, and let's try to find up the infinite sum, right? The infinite sum. So first term will be 8, second term 16, third term 32, 64, 128. Well, this does not seem much different. This is also going to grow and grow without bound to infinity. Boring. Try another one. 4 times 1/2 to the n. Okay, fine. Plug a 1 in. 4 times a half is 2. Plug a 2 in. 4 times a fourth is 1. Plug a 3 in. 4 times an eighth is a half. Well, this is interesting. The numbers are getting smaller and smaller and smaller. Eventually, these numbers will be as good as 0. Think about what that means. So 2 plus 1, 3. Plus a half is 3.5. Plus a quarter is 3.75. Plus an eighth, I'm going to bring out the old trusty calculator here for this one, just so you guys can see everything here. 3.75 plus an eighth, 0.125. 3.875. Now we're going to add a 16th. That's the next term, is 1 over 16. 3 decimals, 4 decimals. Now I'm going to add a 32nd. 32nd. An extra decimal. And the next term will be a 64th. So as good as 0. Every time. These numbers, yes, they are growing, but they're growing at the end of the decimal. Okay, so the numbers at the end are it's getting to be a longer number, not a bigger number. Okay, what has not happened, this 9 has not changed. Yeah, eventually, it might. What do we add last? A 64th, let's add a 1 over 128. 1 over 256. 256. Okay, it's getting there, but it's not growing quickly, and in fact, it's growing at a decreasing rate. This is increasing. I think we all see it's increasing, but it's increasing at a decreasing rate. These guys, I was adding more and more each time. They were increasing at an increasing rate. Increasing at increasing rate. Right, I kept adding bigger numbers each time. Here I'm adding smaller numbers each time. So I'm increasing, but at a decreasing rate, as opposed to increasing at an increasing rate. Okay, so this one will actually head towards a number. It will converge on a number, and let's find out what that number is. I'm going to jump to the next page. We have 4 times 1/2 to the n. 4 times 1/2 to the n. So we have our infinite sums, and if you think about it, we had the finite sums for geometric was 1, what do we have? T sub 1 times 1 minus r to the n all over 1 minus r. Well, now what's happening, since our r value is equal to 1/2, I have the first term times 1 minus r, let's make that a 1/2, to the n, all over 1 minus 1/2. Okay, and this is the important part I'm focusing on right now. 1/2 to the n. As n gets to be larger and larger and larger, the limit as n goes to infinity of 1/2 to the n. What's 1/2, 1/4, 1/8, 1/16, 1/32? We said when r is less than 1, the absolute value specifically is less than 1, this heads to 0. Well, if that guy's out of here heading to 0, this is really just t sub 1 over 1 minus r. So our value, remember our first term here, plug a 1 in, was 2. 1 minus 1/2, that's 2 over 1/2, which is 4. So that sequence, if you look on the calculator here, you can kind of see that's heading to 4. 1 over 512. Then we got 1 over 1024. It's never going to get there. We can get the calculator to get to 3.999999999, but we're going to keep adding things on here. It'll bump the following one up, and the following one, but not the previous one. So these 9s will never bump up. Okay, so it is heading to 4, but it will never actually get to 4. But we say it converges on 4. Okay, so our finite geometric sum. Remember, r, the absolute value of r, the ratio must be less than 1, and that formula for s sub infinity is the first term simply over 1 minus the ratio. And that is our finite geometric sum. Let's look at one more example here before I let you loose. And let's just take anything, okay? Let's say we have s sub n being modeled by, I don't know, here, let's not even do an s sub n. Let me just give you 20, 15, 75 fourths. That should be a 45 fourths. And let's go from there. So our ratio is 15 over 20, or 3/4. Or remember, we could have done our ratio is 45 over 4 divided by 15, which again is 3/4. So first criteria, absolute value of r is less than 1. Check. So now if I want to find the infinite sums, I just need my first term. Oh, look at that, 20 over 1 minus the ratio. Well, it's going to be 20 over 1/4. Remember, dividing by a fraction is the same as multiplying by the reciprocal. So our infinite sum is 80. And if you think about it, I got 20, I got 35. This is what, like 11 and 1/4. So that's 46. You know, we're going to be adding numbers over and over and over again, but they're going to get to 80 slowly and slowly and slowly, but eventually the sum will be 80. That is our infinite sums, and we are talking sequences and series here in trig. Until the next time, see you later.